Hello everyone and welcome back to my Oberheim OB-X restoration series. It's video 3 and we're finally up to the electronics. I have a friend who is doing the power supply on his OB-Xa. So we're going to get the two synths together in the same room and we're going to have a look and a bit of a comparison just with how the supplies are designed, but maybe point out a few other things as well. And then I will also go through in more detail the OB-X supply. So we'll have a look at the schematics and we'll talk a little bit about thermal resistance. It's a really great supply to start talking about that kind of stuff because there aren't many supplies like it. Like in the Yamaha, the early Yamahas, the CS series, there was this nice little well-engineered power supply that looked a bit like a brick, and when you took it out of the synth it was gone. But with the OB-X, if you took the power supply board out of the synth, which would look like this, there's no regulators on it. It's like you don't even have probably a quarter of the supply. It's still all left in the synth. There's regulators on the back, there's regulators inside, there's regulators on the voice cards. It's quite unique. How many voltage regulators do you think are in vintage synthesizers? We'll have a think about it. Say we've got plus 15, minus 15 for the analog supplies. We've got a plus 5 for the digital chips. And that's pretty much the bare minimum, although some mono synths had just 3. The reality is there would be a couple more because the auxiliary circuits, like the analog switches, which quite often had higher than the digital supply on them because it had to pass through CVs. So those two voltages would be somewhere between the 15 and the 5. And they vary depending on manufacturer. So you'd either have plus 8.5 minus 6.5 like Yamaha, or you'd have the plus 10 minus 5, which is used in a lot of synths, or there was like the dual rail 7.5. So there's a whole lot of different versions. But basically those auxiliary circuits, they added another 2 regulators. So most of the time you had 5. So how many regulators do you think the OB-X has? It's 23. So that pretty much blows everything else out of the water. And you might think that that's overkill, but it's really not. This is one of the best design supplies I've ever seen in its management of heat, in its ability to regulate where the voltage is needed most. There were a couple of other synths that had regulators on the voice cards, but the way it's applied here is just wonderful. In fact, the more I look at the schematics of this synth, the more I get an appreciation that Tom Oberheim really did do the best job that he could. I really do get the feeling that there was no expense spared, and that's probably part of the reason why it sounds so good. I'm very privileged to be making videos about the Oberheim OB-X electronics because it really is great. And not only that, as we say in science, I'm standing on the shoulders of giants because there's been a lot of really great work done on this synth already. People like Michael Caloroso have done a fantastic job at documenting how the synth works. So next video, when I get up to the main board, I can do a video that partly involves how the auto-tune works, and I've got a description of it all written down, already done. So as I say on my website, there's 40 years accumulated experience in repairing this synth. And because it's all discrete parts, there's nothing we can't do. I mean, this is a real classic that's great to service, and they're not that common. So that's awesome. So this is going to be great. So firstly, before we start, I have to follow up on something from the first video. You can remember when I was painting the bottom of the OB-X because it was all scratched up, and I was worried that I couldn't paint the whole thing because there was the Oberheim sticker on the back. I was worried that I couldn't get another sticker anymore. And a few viewers have always asked questions about that. And one of them, Manfred, said, "Oh, I've got the font. So we could probably make a sticker. I just don't have the image, the Oberheim image." I thought, I'm sure I've got that image. And anyway, you can search for it on Google. It's everywhere. It's like, and then you just like ring up a sticker shop and ask them to make it. It shouldn't be that much of a big deal. And then he thought, oh yeah. And he came back to me about a week later. And guess what arrived in the mail today? Isn't that awesome? That's so awesome. I'm so proud of this community. We get so much stuff done that we think is impossible. Like, I've seen people reprint, remake the panels for synths. We commonly remake circuit boards. There's knobs being 3D printed. There's not much that we can't do anymore. And to have just a viewer of the channel just go, oh yeah, let's make a sticker, and then one arrives in the mail. I mean, stuff like that, that's awesome. So I'm so glad to have you here because I'm really enjoying this, if that you can tell. So, okay, let's start with the OB-X power supply schematics. Okay, so here's our power supply schematic for the Oberheim OB-X power supply. We start off with our transformer, which is a big one. Thankfully, it is configurable for different mains voltages. Just the two average high and low voltage ranges. So the 230 covers the 220, 240, and the 115 covers the 100 to 120. Incidentally, 230 volts is the standard, the official Australian standard voltage, although the whole country runs on 240. It's the same in Europe, where the standard is also 230, except that everyone runs on 220. So basically, everyone's lying. The only problem I can see in this part of the circuit is that there's a 4-pin plug here on the schematic. So Z1, Z2, Z3, Z4, and mine was 5-pin. Now my OB-X was made about a month after this schematic was released. So if mine is that early, it's likely that a lot of other OB-Xs will have this 5-pin plug configuration. So I'm going to draw this up in Eagle and I'll put it on my website for the 5-pin option. I've drawn it by hand, but it looks a mess, so I'm not going to show you at the moment, but I'll draw up a good one, I'll put it on the website. Now, our secondaries, once they go through the rectifiers, which are our only, how should I put it, our only controversial component, we get plus minus 40 for our main dual rail analog supplies, and we get plus minus 15 from this other secondary. So there's two different secondaries. One gives us a higher voltage than the other one. Now the bridge rectifiers, there's a lot of written word on the internet about these being too small and getting too hot. The junction temperature is probably still okay. If they're too hot to touch, it doesn't mean that they're too hot to run. The analogy is kind of like the car engine. So if I go and drive my car around the block, when I get back, if I touch the engine, it's too hot to touch. But it's actually at normal operating temperature, so it's fine. So there's no point assuming, or I would be wrong to assume, that the engine is broken because it feels hot. Now, it's the same with these bridge rectifiers. The temperature we're worried about is the junction temperature. Now, because these generally last for, let's say, 20 to 40 years, the junction temperature is probably okay. But I would uprate this component anyway, just to be safe, and most of us do, but there's no point putting something in really massive here. So the standard ones are 1.5 amp, and I've changed all mine to 2. And when we do the OB-Xa supply, I'll also put the 2 amp versions in that as well. Now, there isn't really any point doing some thermal resistance calculations on these rectifiers because the voltage drop doesn't change. if we put in a higher voltage at one end, the voltage drop across the diode is still the same. It's still 0.7 volts. So our main way of figuring out whether these can handle more or less heat is just their current rating, because that's the only thing that changes depending on the circuit that we put it in. The voltage drop never changes because a diode is a diode. So if we put in more current, we will need something that dissipates better heat. So we just go on the normal current rating of the rectifier. So moving from 1.5 to 2 amps is fine because they were lasting relatively okay. Most people's OB-Xs and OB-Xas didn't die because of these. Some of them did, but not all of them. So if 1.5 was sort of good enough, 2 is fine. So 2 amps bridge rectifiers can go in here. Okay, so next we have our regulators. So these 3 regulators that you see in the schematic, the LM317, LM337, and the 7805, they offer our plus 19, minus 19, and plus 5 volts, and they are all mounted on the back of the OB-X, and they are in this package, so a TO3 package. The only reason why you would have them in this package, well, there's 2 reasons. One is this package mostly dissipates heat a little bit better. Has a little bit less thermal resistance. So the junction to case for the TO3 is 2.3 degrees per watt. And if we compare that to the TO220, it's around about 4 degrees per watt-ish. Now, it changes on which data sheet you look up, but I'm using the National Semiconductor data sheet. So the junction temperature of this one will increase a little bit more for every watt than this one will. But there's probably a more important reason why these 3 that are mounted on the back are in this package, and that's because this package is easier to mount on the rear. If you put 2 bolts through here, you actually get the pins sticking to the inside of the synth. Whereas if you tried to mount this one on the back, it's difficult, because you don't want to have plugs on the outside. Generally, this package is used internally, so inside the box you'd use this. Now, the heat sinks that are available to both are fairly similar. And the fact that we don't have heat sinks on the outside of objects, of instruments now, means that this one has fallen out of favour, and they're very rare and hard to get. But for the most part, you can get a similar thermal resistance total if you use a big enough heatsink for this one. But the main reason is we don't have heatsinks on the outside of stuff much anymore. So there's less need for this one. So, yeah, that's it, really. And also the fact that the more modern equipment is having less and less power requirements, because they're just built with components that require less power, means that there's less need to dissipate heat. So there's no need for these ones. And in fact, even the TO22 package is becoming obsolete now, slowly. The bigger manufacturers are stopping them and handing them over to the smaller manufacturers. So even these are starting to get rarer. Anyway, all right, so let's move on to the important stuff. So the voltages, we get plus 19, minus 19. This is very rare. The OB-X is quite unique in that the regulation for the voice cards is not done in the power supply. The regulation for the voice cards is done on the actual voice cards. So this plus 19 volts is sent to the voice cards, and the minus 19 volts into the voice cards. And then on the voice cards, you've got a whole lot of other regulators, depends on how many voice cards you've got, doing all the work to bring the voltage down to plus minus 15. Now, that's great because each of these voice cards are now completely isolated from each other and not affected by what happens in the power supply. But it also means that now each of these voice cards have slightly different voltages. So they're running on slightly different voltages. So the voice cards, not only do they differ because of all the analog components that are on there are different tolerances, but the power supply on each individual voice card is a slightly different tolerance. So that accentuates the difference between voices. And that doesn't happen in synths like the OB-Xa, where all the power for the voice cards comes from a single line from the power supply. So the power supply generates plus minus 15 that goes to the voice cards, and that's common between all the voice cards. Not the case in the OB-X. What else have we got on the back? We've also got a 5 volt on the back. So that rounds out our big heat sinks. And then internally we've got 4 regulators. So we've got the -5, and we've got +12, which is for the ROMs. We've got the +-15, which is basically now for very few analog components. Right, so there's one circuit that's left, and that's this one here. And wow, is this an interesting one to talk about. Okay, so in very old synths, when we had our patch memories stored on separate chips to our processor, which is not what happens these days. The patch memories these days are stored mostly on the same chip itself, on the flash memory on the main processor. But in the old days, they were separate chips. And the problem was when we shut down the synthesizer, all the digital circuits go a little bit crazy as the voltage drops. So it's a really good idea to disable our RAM ICs so that our patches don't get written over with all this data traveling everywhere throughout the buses as all the chips go a bit nuts as they shut down. So what we do is we put in a voltage monitor circuit which outputs a 5 volt line which enables our RAM chips. But this 5 volt line is actually derived from a voltage that shuts off quicker than our normal 5 volts. So if you have a look here, it's derived from our 19. So when we shut off the synth, what will happen is this 19 volt rail will drop quicker than our 5 volt will. Now there's a lot of reasons for that. One of them is just the ratio between our in and our out voltages on the regulators themselves. So this is about 2-to-1 ratio. And this one over here is 3-to-1. So it's going to take longer as our voltage drops on this side. It's going to take longer for our voltage to drop to hit the 5 volts than it will to hit the 20, because we've only got to go halfway before we start not being able to put power here, whereas we've got to go 2/3 of the way down to not put it here. Now the loads are different and also the capacitances are different. But you'll notice the capacitor, the largest capacitor we've got on this whole board is actually on the 5 volt rail. So our 5 volts is designed to last longer. So our 19 volts will start dropping quite quickly and it'll be shut off when it reaches around about not very much lower than 19. So basically this circuit is just a fast shut off for a 5 volt supply, whereas this one is going to be slowly traveling down as this big capacitor drains. So what that allows us, it allows us to shut off some chips before others. So we get to do a staged shutdown. Now this circuit is actually called the power up, or the power up monitor circuit. It's probably best to just demonstrate what it does. I can set it up now in the OB-X with a couple of LEDs and we can watch the staged shutdown just visually. I think that'd be pretty cool. So let's do it. Okay, so I've set up a breadboard here with 2 LEDs on it to give you a visual demonstration of how the power up monitor circuit works, or at least what it does. So the LED on the left will show us that power up monitor signal, and the one on the right will show us the actual voltage on the 5 volt line. So when we turn the synth off, we should see the power up monitor circuit detect that, and this LED should shut off, which would shut off the write lines to our static RAM, meaning that those chips can no longer be written to and our patches are safe. Now this is the same, exactly the same concept as the memory protect switch. So when we switch the memory protect off on the OB-X, it's exactly the same as the power up disabling the write lines to the static RAM. So we're imitating that memory protect switch during a power off. So let's turn the OB-X on. Okay, so we've got the 5 volts to our lines that enable our writing to our static RAM, and we've got the 5 volts onto all our CPU, all the digital logic, all that kind of stuff. Now, because I don't have the main control board in, there's not much load on the power supply. So we'll get a really good opportunity to see the time delay between these two circuits. Now, if I had the control board in, there'd be a lot more load, and the difference between these would be almost too fast to see. So it's a good opportunity, the way it is now, to do this demonstration. So if I turn the switch off, okay, 1, 2, 3, and off. We're off now. Our power up circuit should now detect that we're off. Yep, and it's gone. And see how the 5 volts is still on? And that'll slowly fade out now. See how long that's taking to go away? Now, during that time when it's fading out, we'll get to an area where the digital chips won't quite know whether they're on or off. They'll be like in this in-between state, in a no man's land. And that'll happen at slightly different times for slightly different chips as well. So the whole circuit can go a bit nuts. But because we've already disabled our write lines, those sporadic ones and zeros that happen on the data bus, they'll be blocked. So let's just view that again and just have a look at the slow fade out of the 5 volts and how fast the power up monitor line turns off. Okay, ready? 1, 2, 3. Hang on, I'll just focus the camera a bit more. Okay, ready? 1, 2, 3, off. Boom, gone. And now look at this, we're still on, we're fading out, we're fading out, we're fading out, fading out, fading out, fading out, fading out, still there a little bit, fading out, now we're gone. So you can see the benefit of this circuit. It makes such a massive difference to the stability of our memory. Now, if you replace this analog supply with a switch mode supply, the switch mode supplies turn off faster. So even if you recreated this circuit, you're not going to have the same amount of time available to you, because the capacitance, generally speaking, in switch mode supplies is a lot less. So you'd need to modify this reset circuit. And in some cases, it won't even work. So I'm a big fan of the old analog supplies for old analog synths, because we can do lots of cool stuff like this. Because we've got so much time, comparatively speaking, it happens much faster when you've got the main board in, but comparatively speaking, we've got a lot more time with an analog supply to shut stuff down properly than we do when we've got a switch mode supply. Now, in modern synths, it's fine to use the switch mode because a lot of our chips have these memories built into them now. So the chip itself can manage its shutdown. But if you take one of the new supplies and put it in an old synth, that's when you've got problems, because we need to stage our shutdown. And if we don't do that, we can have massive issues. Now, the only other thing that's left here is our battery backup for our RAM. And the RAM that we're using, the SRAM, it will hold its memory as long as there's a voltage on this line that's higher than 2 volts. So our battery's 2.9, but there's a diode in the way, it drops about 0.7. So you've got a little bit of buffer here. But you don't want this to drop too much because we won't be any higher than 2 volts, and then we'll have to replace the battery. Alright, so let's have a look at the OB-X and the OB-Xa, and we'll compare the two. So as you've seen in the OB-X, the supply is rather small, and its main job really is just to supply the 19 volts to the voice cards and the 5 volts to all the digital stuff. Now in the OB-Xa, it's a little bit different in that there's no 19 volts generated on the power supply. So the 15 is generated here and then it's sent to the voice cards. So you'll notice on the OB-Xa voice cards, there's no regulators for the plus minus 15 volts. And that means that the power supply has to supply a lot more current on the 15 volt rails now, because it's its job to supply all the power needed for all the voice cards. Whereas previously on the OB-X, you'd have the 19 volts going to the voice cards, and then the voice cards would do their own 15 volt rails. So if we compare the OB-X voice card to the OB-Xa, you can see, hang on, just focus the camera. You can see the two regulators here. So it just means that the 15 volts, we just have to make sure that all the capacitors and all the regulation is really good on the existing supply, because it isn't being done locally on the voice cards now. So we've got a bit to do with this power supply. Replace the capacitors. We'll also replace the bridge rectifiers. And we may even do a couple of other things. We'll leave the regulators on the back, which is what I did with mine. I left my regulators on the back because they're fine. They're also quite rare. So even though I've bought spares, I'm not going to use them. I'm just going to keep them as spares. So we'll do the same thing here. And that simplifies the job. So let's get the board out. Okay, so here is the OB-Xa supply. And you can see from the back that there's a bridge rectifier here that's gotten pretty hot. Now this one is DR1, which is on the 5 volt rail. And someone has replaced it before. So if we look at the other side, you can see it's bigger than the other two. Now, this one was hard to find information on, but I think it's a 1.5 amp bridge rectifier. Now, the ones that we've got to put in are all 2, so we will replace all 3. I don't think there's any point going bigger than that for the moment. I guess we'll just see how it goes. And of course the caps have to come off. And it would be nice to put new trim pots in, but I don't think I've got any at the moment as replacements, so I'll just leave them in for now. So as long as we do the caps and the bridge rectifiers, that's kind of the basic stuff done, and maybe the smaller electrolytics. But I'm not going to change the values of these because I don't know how that power off monitor circuit works in the OB-Xa yet. So it's good practice if you don't actually know how the electronics work to try and leave the power supply alone and don't make these capacitors any bigger, because you could mess with that delay circuit which turns the static RAM off before the power goes down to all the logic. So until I investigate the OB-Xa, I'm going to keep this as normal, as it is. Okay, so all the capacitors and the bridge rectifiers have been replaced, and the solder on the headers has been redone. It's a common failure point is the solder on the connectors gets dry and it can disconnect, particularly on the memory mode power supply. That's the most common problem with it. But this one was okay, but I've done them anyway. And you can see that when somebody else has replaced the bridge rectifier, the solder that they've used has a lot of flux in it. So this all needs to be cleaned off. So my joints weren't too bad, but yeah, the other one needs to be cleaned. So usually I just use isopropanol and a toothbrush, and I just keep spraying it on and brushing until the flux is gone. And don't be afraid to use a lot. Do jump. Come on,
I
do
can't
jump.
play it very well.
Just a little bit. Just
I'm really
just
shit
even
at
just
it.
a shit version.
Can we just practice it, dude?
Go, practice it.
Alright, sorry, try it now.
Go.